upon I. FBT they have given as 40 is equal to m into y top, that is 40 divided by I, that is 5.32 into 10 to the power 6. Okay, so we can get the value of FBT of we can get the value of m. Okay, similarly FBC, that is equal to m y at bottom upon I. So you can get the values as FBC is given as how much? 70, that is equal to m into y bottom they have given as 80 upon I, that is 5.32 into 10 to the power 6. Okay, so we can get the values of m from both these values, whichever is minimum that we have to take. Okay, so after getting that particular value we can equate to our bending moment obtained at B. Okay, so from that particular thing we can find out the value of bending moments, and whichever is minimum that will take, and we will equate it with the bending moment at point B. So you'll get the unknown value of W, and the answer obtained is W, that is equal to I think we have to calculate the value of W from that particular thing. So we'll calculate the value of W. Now if the cantilever beam is there, we are basically taking it as what? We are taking it as compression at the bottom and tension at the top. But if it is a simply supported beam, we are taking the compression at the top and bending moment at the bottom. So now in this particular case, when it is a overhanging beam, what we have to do? We have to take this as a top, we will take it as compression, and bottom will take it as tension. How we will decide that? So to decide that, we have to see it is producing which type of moment, right? The diagram is like this, that is the diagram is in this particular way, right? And load is coming like this, and we are taking moment at this particular point. Okay, so how it is going to rotate? It is going to rotate like this, right? So at top it is what? Hogging. So top will be subjected to what? Tension, and bottom will be subjected to what? Compression, right? Again I'll explain. See, this is like this. I'll draw a big diagram so that you are able to see, right? Now when the load is converted in terms of a movement, it will rotate like this, and it will, at this particular point, it will be a which moment? Hogging moment. So outer is top is tension and bottom is compression. That is why if you will see that what I have taken FBT. FBT is what? Tension. So what I have taken? Y at top, because tension is at top. Is it clear? Why I have taken that? Similarly, compression is at bottom. That is why I have taken what? M Y bottom. Okay, so that is clear now. Okay, what we have to take? We have to take Y top and Y bottom, as tension is at top and compression is at bottom. Second thing is, we are getting the values. So for this we are calculating, and we are getting the value as 1.849 into 10 to the power 6. Okay, and what will be the unit? Newton mm. And for this case we are getting the value as 6.81 Mostly it is this, or you just counter 6 point. I'll just calculate it. 40 will cancel out, so it will be 5.32. Sorry, this will be 5.32 into 10 to the power 6, and this will be 70 upon 80 into 5.32. So this is 4.65 into 10 to the power 6 Newton mm. Okay, this is m1, this is m2. Now moment of resistance, that will be minimum taken, okay, of both the values. So which is the minimum? m2 is minimum, so we will take m2 as minimum value, and that is equal to 4.65 into 10 to the power 6 Newton mm. Okay, now I am interested in finding out the value of W. So I can equate this m2 with the bending moment I have calculated at point C. So what is the bending moment at point C I have calculated? That is bending moment at point B I have calculated as W kilonewton meters. That is W into 10 to the power 6 Newton mm. Okay, and moment of resistance minimum we have obtained as 4.65 into 10 to the power 6 Newton mm. So I can equate equation 1 with equation 2. Okay, so W into 10 to the power 6 is equal to 4.65 into 10 to the power 6. So we get the answer as 4.65 kilonewtons. Okay, it was a big problem, but a very important problem, because you can see we have to think it is hogging or sagging. Depending upon that, we have to take the values of the y bar, right? And this all things are important to understand, because at point this, the bending moment is hogging, so tension at top. So now if I want to draw a bending stress diagram for this, it is in this particular way, right? It is a T shape like this, right? This is our CG point, so I can show this as neutral axis. This is 80 mm, this is 40 mm. Okay, we can extend these lines as well as neutral axis. We'll draw vertical line, then tension will be at top, so I can show FBT. Over here neutral axis, no load, 0, compression. Okay, FBC. So this is our final diagram. Okay, so I think I have taken or tried to cover almost all types of problems. Now we go to our another theory which is left out, that is the suction modulus. Okay, so to study the suction modulus, we are going to use our PPTs. So to start with, first of all, what do you mean by the term suction modulus? Okay, now in a very simple language, if I want to explain the suction modulus, so suction modulus is basically a property, another property of a beam, in which when we are designing, it plays a very vital role, right? That means if the beam is to be designed, then we have to take a lot of care on the depth of the beam, and to study that, we are going to study the suction modulus. Also, suction modulus plays an important role for the strength of the beam. Okay, so what is there in the PPT? We'll just go through it. It is another property used in the beam design. The section modulus of the cross-sectional shape is of significant importance in designing beams. It is a direct measure of the strength of the beam. A beam that has a larger section modulus than another will be stronger and capable of supporting greater loads. That means if I want to find out that which beam will have more capacity to take load, if I know the value of section modulus, I can easily say that the section modulus having much more greater as compared to the another one will give more strength. Okay, it includes the idea that most of the work in the bending is being done by the extreme fibers of the beam, that is the top and the bottom fibers of the section. The distance of the fibers from the top to bottom is therefore built into calculation. Right now, what does this PPT wants to say? You can see over here, when we are finding out the values of bending stresses, we are using one term, that is distance of extreme layer with respect to neutral axis, right? So this is the extreme layer, and the distance of this extreme layer with respect to neutral axis is nothing but y. So this y plays a vital role when we are calculating the value of section modulus. Okay, so that is what we have to consider. The elastic modulus is denoted by Z. To calculate Z, the distance y to the extreme fiber from this centroid must be found out so as that is where the maximum stress could cause failure. So we have to first calculate the value of y. Okay, and y is nothing but the distance of the extreme fiber with respect to neutral axis. I have taken a very simple problem, one of rectangular section which I have shown already in this diagram, and second is of I section. Right now, I section, both the section, you can see what similarities there in this particular section. Both the figures, what is the similarity? Can you guess? Can you guess? Yes, it is a symmetrical section. Right, symmetrical section means the distance of extreme fibers for both the cases will remain same. Right, that is, but if my section is of this particular shape, right, will I get a symmetrical section? No, my CG will pass from somewhere over here. It is not giving you the mirror image. Right, so the value of y will be different, and I will have to write down y bottom, y top, whereas in this case, as it is symmetrical, I will have to only write down y. So y plays a very important role in section modulus. Okay, now if I want to define a section modulus, how can we define a section modulus? So section modulus is basically denoted by Z. In some cases it is also written as elastic modulus. So section modulus Z is defined as the measurement of strength, and mathematically it is given as the ratio of moment of inertia to the distance of extreme fiber with respect to neutral axis. So we can say that the section modulus Z, that is equal to I upon y, where I is moment of inertia. What is the unit of moment of inertia? Unit of moment of inertia is mm to the power 4. What is y? Distance. Which distance? Distance of extreme layer with respect to neutral axis. So its unit is mm. Now tell me one thing, how do you locate neutral axis? How do you locate neutral axis? The neutral axis is located by finding out the centroid of the section. If you go through all the numericals that we have solved, we have found out the CG of the section, and from that particular CG point, the line is passing, and that line is nothing but the neutral axis. Okay, so to locate neutral axis, we have to calculate the CG or the centroid of the section. Okay, so now what will be the unit of Z? So mm to the power 4 mm, so we'll get mm to the power 3. So the section modulus unit is mm to the power 3. Now we are going to derive the section modulus for different shapes. So what is the section? All right. Now when I come to the section, what is the section? So the first is the size and the shape of the piece of the material used is section. Okay. Now material used. Generally in our civil engineering works, we use the material like timber, wooden beams, or we use steel beams, that is I talked T section, I section, and or we use a RCC beam. Okay, so the size and the shape of the piece of the material used, that is for timber, generally it is a rectangular shape. For steel sections, we use generally I sections or T sections, or channel sections or angle sections. And for concrete, we use either a rectangular section and often a T shape. Okay, you can see this person with the I section over here. Okay, why different shapes and sizes? Why not we go only for a rectangle, or only for a circular, or only for a triangular? Basically, what are the different shapes and sizes, and which basically shape or size we have to use is important, right? So what shapes are possible in the material, right? If I suppose take a wooden beam, it is possible for me to cut it in a rectangular, it is possible for me to cut it in a circular. Circular will be difficult, right? So generally when we have got a wood or a timber, then we go for a rectangular or T shape. Okay, then what shapes are efficient for the purpose, right? Now if I have a very small room, and in that particular small room I will not go for an I section, I will simply go for a rectangular section. So the purpose is also important, aesthetic view is also important, and efficiency is also important, plus economy, right? So we have to see all these three things: economical, then efficient, then aesthetic. Okay, and the purpose is solved. So obviously bigger is stronger but less economical. Okay, so you can see over here we have got different shapes. You can